Derivation of formula of elastic potential energy. It is the energy stored as a result of deformation of an elastic object, such as compression or stretching of a spring. Let us understand the diagram here. We have got a spring that is attached to a wooden block. When the spring is relaxed, no force is being applied on it that compress or stretch it, then the block is here. We apply a force that pushes the block to the left. So finally the spring is compressed like that. So the distance that is compressed is shown here. As we apply a force on the block to the left, the block is displaced to the left, so there is work done on the block, and as a result elastic potential energy is stored in the system. Why can we write W equals delta E? Because this is work energy theorem. I am replacing delta E by delta EPE, change in elastic potential energy, because this is the only change in energy that is happening. We move the block very slowly, so initial and final kinetic energy is 0, and the block is also not gaining any height. Let us expand delta, which means final elastic potential energy minus the initial elastic potential energy. When the spring is relaxed, there is no elastic potential energy stored in the spring. So we can put EPEI to be 0, because elastic potential energy in a relaxed spring is 0. So that's the final expression. Work done equals to the final elastic potential energy. I am going to label this equation 1. Let us look at a graph of force versus elongation of the spring. This part of the graph, which is shown in first quadrant, is actually the same as the spring Hooke's law lab that you did in the class. What is this graph showing? That if you apply a force, it elongates the spring such that the force is proportional to the elongation, and we get a straight line if we join these data points, and the slope of this line gives us the spring constant. What is this dotted line? It is showing us that if we apply force beyond this point, the spring might go beyond its elastic limit and will not come back to its original shape. This proportionality between force and extension also works between force and compression. If we apply force to the left of the spring, it will compress the spring, and still the compression and force will be directly proportional. This can be written mathematically as force on the spring equals K times X, where K is the spring constant, where X is either the extension or compression of the spring. This equation is also known as Hooke's law, which says that force applied on a spring is proportional to extension or compression of the spring. If we look at the graph in the first quadrant, we see that on the x-axis we have got displacement, and on the y-axis we have got the force. So we will apply work done on the spring and look at the definition of the work done, which is work done by the force is equal to the area under the force versus displacement graph. Here the area under the force versus displacement graph looks like a triangle. The base of the triangle is displacement or extension x, and the height of the triangle is the force, which is kx. So from the force versus displacement graph, we can write that the work done is equal to the area, which is half fx. The reason of writing this equation is because area of a triangle is half times base times height. Base here is x and height is f. We replace f by kx because we are using equation 2, which is Hooke's law. Let's simplify it, and it becomes half kx square. Let's label it as equation 3, and now compare equation 1 and equation 3. Both the equations on the left hand side give us work. So first equation says that work is equal to the final elastic potential energy stored in the spring, and the third equation says that work equals to half kx square. Because left hand side is same, we compare these equations and we conclude that the formula for elastic potential energy is half kx square. Elastic potential energy is a type of energy, so its units would be joules. So the formula, when simplified, should also give us units of joules. Half does not have any units. K has units of newtons per meter because it is the slope of force versus extension graph, and x has unit of meters. So if we write all the units and simplify, we get Newton per meter from K and meter square from x square. This simplifies to newtons times meters, which is equal to joules.